The topic of presentation is assessment of trends in the functioning of the grain industry of the European countries using ARDL modeling. Regression modeling is used to estimate, planning and forecasting of agricultural production, but can be complicated by multicollinearity, autocorrelation, and structural shifts. ARDL is an approach that allows to take into account the relationship between factors in production. This method allows for the inclusion of non-stationary variables at the I0 and I1 levels. ARDL reflects the lack of effect of factors on the dynamic of variables, including lags, which allows to take into account the correlation between them. A dynamic error correction model can be built from RDL to integrate short-term dynamics with long-term equilibrium without losing long-term information. There are a number of approaches to formalizing dynamic relationships. In particular, one of them is the use of the lag of the resulting indicator as an independent variable simultaneously, with independent variables characterizing the processes in the current period. Formula 1. It is recognized that a change in the regressor "x" may have consequences in other periods of time, and therefore the consequences of management decisions in the current period may be unpredictable and affect production results not only in the current period, but also in subsequent periods. Instead, taking into account the influence of the lag of the resulting indicator on its current value, we have a dynamic model with one independent variable and its lags. Formula 2. After combining Formula 1 and Formula 2, we obtain a dynamic model with lag-dependent and explanatory variables. This model is an autoregressive distributed lag model that includes lags for the factor and outcome components. In general, in its expanded form, it can be represented as an infinite lag model in which the autoregressive characterizes the effect of its lag on the outcome function, and the lagged component reflects the effect of lagged x. The theory of production functions is based on a model that analytically describes the relationship between the accumulation of resources, their consumption, and output. For wheat production, the outputs are the output in physical or value terms, and the inputs are the consumed resources, operating costs, or both. An important element of resource potential is soil fertility. Their direct inclusion in the regression model is quite problematic, given the complex nature of the concept, and their reduction to an economic equivalent requires a number of assumptions, which complicates the model itself and reduces the quality of the forecast. Resource potential and production technology are the main components of the production potential of agricultural sector. Their quality affects the culture of farming. Crop yields for previous periods can serve as an indicator of farming quality. This allows us to use an autoregressive production function to predict production results. Traditional production functions are characterized by a mutual correlation between the cost of inputs, machinery maintenance, and others. The difficulty in formalizing inputs and outputs is compounded by the consideration of the aftereffects of fertilizers, in particular phosphate fertilizers, which affect soil fertility. To overcome these problems, a multivariate co-integration RDL model can be used. Accounting for the feedback of technological and economic efficiency on costs is important, especially when considering the price of a product. This price affects the level of unit costs, which can increase or decrease productivity in the next period. In the RDL model, it is reasonable to include lags of the selling price together with lags of yield and costs. However, the inclusion of both prices in the model may worsen its quality due to the complex dynamic relationship at the I2 level. Therefore, price dynamics were replaced by the indicators of cost recovery for the production of different wheat varieties, which are reliable determinants of cost in the current period. Taking into account the inflationary nature of input prices requires that costs be brought into comparable terms. Due to the restrictions imposed by the full-scale war in Ukraine, data from European farms were used to analyze the costs of wheat production. In particular, the data on specific costs of wheat production of French farms are available on the Eurostat website. Thus, our model included indicators of yield, production costs and constant prices, and payback of cost of production and marketing of soft and durum wheat. The descriptive statistic of this dynamic series and their graphical integration show a trend of increasing return on cost of durum wheat production and stationarity of other series. At the same time, against the background of relatively higher variation of the indicator of costs at constant prices and their payback in the production of durum wheat, the yield and payback of cost of soft wheat production is moderate, which positively characterizes the common agriculture policy of the European countries, which prevents the crisis of overproduction. The next step was to test the series for stationarity. The ADF test for the variables included in the model showed that the dynamic series of durum wheat yield and profitability of sales are stationary at the level I0. On other hand, the dynamic series of production costs per 1 hectare of wheat crops and the profitability of soft wheat sales are integrated at the first order I1. The analysis of this unusual data in the EVU's 12 software environments showed that the most appropriate model is the ARDL model with the lowest AIC value, with a 3-year lag in yield and 4-year lags in the payback period for durum and soft wheat production costs. Instead, according to the chosen criterion of information similarity, the inclusion of lags of production costs per unit of crops in constant prices of 2010 is inappropriate, which requires further research. The modeling results show differences in the impact of lags of individual variables on yield dynamics. In particular, the first lag of the payback period for durum and soft wheat production costs, as well as the constant, had a p-value of 1%. The first lag of yield and the second lag of cost recovery for durum wheat production were significant at up to 5%. In turn, the current cost per unit of crops in constant 2010 prices, the second and third yield lags, the first and third payback lags of durum wheat production, and the second and third fourth payback lags of soft wheat production were significant at the 10% level. In contrast, in the indicators of cost recovery of soft wheat production in the reporting year and its first lag are not significant. The next step was the marginal test for the presence of a long-term relationship. It was found that the value of the F statistic exceeds the upper bound for I0, which suggests the presence of a long-run relationship at the 1%, 5%, and 10% significance levels. In view of this, we formed an error correction model that allows us to estimate how much of the disequilibrium is corrected. That is, how much of the previous period's disequilibrium is corrected in the current one. It is recognized that a positive ACT coefficient indicates a divergence and a negative one indicates a convergence. If it is equal to 1, then 100% of the deviation is adjusted during the period and the adjustment is instantaneous and complete. If ACT equal to 0.5, then 50% of the adjustment occurs each period. The value of ACT equal to 0 indicates that no adjustment occurs, and it cannot be said that there is a long-term relationship. For the analyzed model, the ACT is negative and highly significant, indicating convergence. Thus, it can be argued that 246.6% of the adjustment from short-term to long-term occurs in less than 4 months. Thus, the construction of a production function for the grain industry takes into account internal and external factors of production organization, but may face obstacles, such as the correlation between land fertility and operating costs. The non-synchronized dynamics of grain prices and input prices complicates modeling. One way to overcome these obstacles is to use an autoregressive depend lag model. The variables of the wheat yield model were indicator of operating costs in constant prices in 2010 and the payback of wheat production costs for 1990 to 2018, as well as lagged yields in the years preceding to the reporting year, which allow to take into account the efficiency of using the production potential of the grain industry. Structural gaps in the dynamics of prices for purchased inputs and wheat grain in the domestic Ukrainian market in 1990 to 2018, which led to its non-stationarity and prompted the construction of a model based on the indicators of French farms for the same period. The modeling showed the unequal influence of individual factors on the yield dynamics. In particular, the p-value at the level of 1% is observed for the return on costs of producing soft wheat grain in the reporting year. its first and third legs, and the second and third legs of the return on cost of producing during wheat. The sign of the regressors alternates due to a decrease in prices in years of excessive grain production and an increase in prices in lean years. The value of the unit cost regressor is also negative, and its legs were not included according to the AIC criterion. The reason for this is the industrial nature of the technologies used. Under such conditions, further research should focus on the behavior of lagged cost values and the impact of the common European policy of regulating agricultural productivity on their formation. Thank you for your attention.